Hi, welcome to the eighth video lecture. Today we're going to talk about diagonalizing our operators. Just to recap, last lecture we looked at what operators were, and that was essentially they were mathematical objects that act on kets and result in another ket. So, and our observables are represented by operators. This was discussed in some of the postulates. So basically, if we have some S sub z or the operator representing the measurement of the z component of the spin angular momentum, it operates on some general ket, and the result is another ket. We talked about how we can represent these as matrices. So that same equation we just talked about, written in matrix notation in the Z representation, would be a 2 by 2 matrix for the SZ operator acting on our generalized ket represented as a column vector, and it would produce some other ket, some other general column vector. The other thing we mentioned is that there are things called eigenvectors and eigenvalues for a given operator, where eigenvectors are kets that, when acted on by that operator, don't change. They're essentially the same ket with some multiplicative constant that's referred to as the eigenvalue. So in this case, SZ acting on our spin up state produces our spin up state times some constant. Which was h bar over 2 for this case. And in matrix notation, that looks like this. The S sub z operator, again, that 2 by 2 matrix, operating on the unit vector that is the spin up state, equals h bar over 2, just a constant, times that spin up state. One thing we noted is, again, depending on the representation you're in, so in this case, we've been doing everything in the z bases, the operators, if they're represented as matrices in their own bases, are always going to be diagonal, and the eigenvectors are always going to be unit vectors in their own bases. Now, today what we're going to look at is sort of coming about this the opposite way. When we talked about operators last time, we started with SC and something that we already knew the eigenvalues and eigenkets were. What's more often the case is you're given some other operator, say S sub x or S sub y or some other operator, you're given the matrix representation in that basis, and you have to figure out what are the eigenkets or the eigenvectors and the eigenvalues for that, which is a process called diagonalization. How do we diagonalize these? Which you're probably familiar from your mathematical physics class or some of your linear algebra classes if you've taken it. Anyway, that's what we're going to cover today. So let's say we're given some operator A. How do we diagonalize that? Well, in ket notation, the operator, the eigenvalue equation for that operator would be operator acting on some eigenket equals that scalar constant times that same ket. And if we bring everything to one side, we end up with just that operator times that ket minus that constant times that ket. In matrix notation, we get the matrix representation of our operator A and all its n by n terms multiplied by the general, whatever that eigenket or eigenvector would be, is equal to a constant times that. Bringing everything to one side, just bring it over, we get that minus. And then we can sort of factor this all out, and so we just have one big matrix multiplied by our eigenvector, and along the diagonal we have minus that constant through there. This is essentially what we call the secular equation. Written in ket notation, it's the matrix minus the eigenvalue, whatever that may be, times the identity matrix, all operating on that eigenvector equals 0. So hopefully this is somewhat familiar from your math phys or linear algebra courses. The gist is this has solutions if the determinant of this matrix is 0. So that's essentially what we do with these things. So let's look at an example. So let's say I've given you what the SY operator is. That is the operator corresponding to the observable of the spin angular momentum projected in the y direction. So we want to know, we've been told that that's the matrix representation of this operator. We want to determine what the uh, eigenvalues, what are the possible results of that observable measurement of that observable would be, and what the eigenvectors are that correspond to them. Well, we can write our eigenvalue equation as this, right? Typically, it's common to use lambda as a symbol for eigenvectors and the corresponding eigenvalues. So we have Sy operating on some unknown eigenvector. It's going to be equal to some unknown eigenvalue times that same eigenvector, right? If we bring everything over, this ends up being Sy minus lambda times the identity matrix times that eigenvector is equal to 0. And as we just discussed, this has solutions if the determinant of Sy minus lambda is equal to 0. So essentially, that's what we have to do. We have to take that determinant. How do we do that? Well, this matrix ends up being negative lambda minus I h bar over 2 h bar over 2I minus lambda. And taking the determinant of that is just negative lambda times lambda. That gives us lambda squared minus, well, we have minus negative I squared. So this is plus I squared h bar over 2 squared. If that equals 0, right? Or lambda squared minus 1 minus h bar over 2 squared, which this has solutions. Lambda equal to plus or minus h bar over 2. So really quickly, we already kind of knew this from our discussions of the Stern-Gerlach experiment previously. We knew that spin was quantized no matter which direction you measured it in units of plus or minus h bar over 2 for these systems. So it's good. We just determined what the eigenvalues for this operator, this spin in the y direction Sy operator is. Right. So now we have our two eigenvalues, plus or minus h bar over 2. Now the question is, well, what are the eigenvectors? So to do that, we just return to our eigenvalue equation. We have Sy acting on our eigenvector is equal to h bar over 2 for the first eigenvalue times that eigenvector again. If we write that in our matrix representation, we have h bar over 2, 0, negative I, 0, times that arbitrary vector that we're unsure of, a, b. The column vector is equal to h bar over 2 times a, b. The h bar over 2's can just cancel out, and we're left with negative I b is equal to a, or I b is, sorry, I a rather, rushing here. I a is equal to b. Those two equations are not actually independent, so we really only have one equation here. Multiply by I, and you multiply this equation by I, and you get this equation. So they're not linearly independent. We have one equation and two unknowns, so we need something else to really fully determine what this eigenvector is. The way we go about that is we recall that all of these vectors are normalized. So that means if I take the inner product of that eigenvector, I must get 1. So in the matrix representation, we have simply the transposed complex conjugate of our column vector times our column vector. This has to equal 1. And if we actually do that multiplication, we end up with a squared b squared is equal to 1. Right? If we give us a little more room here. Just plug in, if you recall, uh, that equation we have here. If we plug that in for b, we end up with a squared plus this ends up being ib squared. So b squared, sorry, it's equal to 1. Rewrote the same equation, forgive me, plus ia squared is equal to 1, which is just 2a squared is equal to 1 because this I in the complex conjugate of IA comes out. So this tells us A is equal to 1 over root 2, right? Which would imply B is equal to IA, so it would be I over root 2. So that means that our eigenvector for the h bar over 2 eigenvalue is represented by the column vector 1 over root 2 I over root 2. Or written another way, just 1 over root 2, 1 over I times that. Sorry, I got a little sloppy in here, but hopefully you're able to follow it. It's something you've hopefully done in your math, physics, and linear algebra course again. But what we've essentially just shown is that for the h bar over 2 eigenvalue, the corresponding eigenket, which we previously labeled the spin up in the y direction, can be represented as 1 over root 2, 1 times I. Or if we write that eigenket in the z bases in ket notation, this ends up being plus plus I minus all over root 2. If we do the same thing for the minus h bar over 2 eigenvalue, you can follow the exact same process, and the eigenket for that will end up just being in the matrix representation 1 over root 2 again, 1 minus I, which in the ket notation, sorry, miswrote that there. In the ket notation, that is plus the spin up in the z direction minus I, the spin down in the z direction, all over root 2. So hopefully that is a clear enough result, a little example to work through. The idea is if you're giving some operator, we started off, remember, with this operator here, just telling us that that is our SY operator. We were able to figure out what our characteristic equation is, and then following this process and making sure they're normalized, solve for what our eigenvalues and eigenvectors are. Next class, we're going to just build on, discuss some other operators that we have, essentially the spin projection in any arbitrary direction, and we'll move on from there.